Hey everybody, in this video we are going to be talking a lot about Gibbs free energy, indicated by the letter G. So once again we have another type of energy we are talking about, and it's slightly different but related to enthalpy, which is another type of energy we learned about 2 videos ago. No, actually not 2 videos ago, many videos ago. So Gibbs free energy actually represents the amount of free energy. So free energy and Gibbs free energy mean the same thing in the context of chemistry. So it represents the amount of free energy that can be used to do useful work. So useful work is work that is useful. Now in the context of chemistry, that means that it is work that can be used to move a reaction forward. And that sounds like spontaneity, and we will see how ΔG is very related to spontaneity very soon. So let's think about what a negative ΔG means. A negative ΔG means that the initial G has decreased to produce a final G, and the final G is less than the initial G because, well, let's just say the reaction might have lost some Gibbs free energy, and this decrease in Gibbs free energy is a negative ΔG. So it's a negative increase or a decrease. So a negative ΔG value indicates that the reaction has released some useful work, just like how a negative ΔH means that the system is exothermic, so the reaction will release some heat, which heats up the surroundings. So in this case, we are talking about G, so we're talking about a release of free energy or useful work. So if the reaction releases some useful work on its own, then this useful work can be used on the reaction, and it kind of gives the reaction the energy to continue on its own. Now, what about a positive ΔG? Well, a positive ΔG indicates that we won't be releasing any Gibbs free energy. We will instead need to absorb Gibbs free energy for this reaction to start up. Now, because there's no Gibbs free energy that's just floating around ready to give the reaction a kind of kick to start, that means that the reaction has to absorb useful work from external sources to continue. So for a negative ΔG, the G that is released by the reaction can actually start the reaction up and kind of keep it going. But for a positive ΔG, what ends up happening is that you don't really have any free energy that's being produced to move the reaction forward. Instead, you have to constantly put in energy from external sources, which we will talk about very soon. So it's not self-sustaining, which is why it's non-spontaneous. And spontaneous reactions are self-sustaining, which means that in this case, free energy is constantly being released and it's constantly working on the system to move it forwards. But that doesn't happen here. So let's talk about electrolysis. We will learn about this way later, but electrolysis is essentially a type of non-spontaneous reaction. And if you can look at the word electro and lysis means we are breaking down something with electricity. So in this case, one of the most common electrolytic reactions is converting water into O2 gas and H2 gas, and I'm not going to balance this reaction. So the electrolysis of water is actually a little interesting because it involves pumping electricity through water to have it decompose into 2 gases, which we are very familiar with. Now, as you may notice, water doesn't naturally decompose into these 2 things, so we know that this reaction is non-spontaneous. Well, at least at 25 degrees Celsius, which is the conditions that, things are usually at. So this reaction is obviously non-spontaneous. So how does this reaction occur? Well, we can force it to happen using electricity. So electricity would be an external source of energy that would cause this reaction to happen, even though this reaction has a positive ΔG value, which indicates non-spontaneity. Now, even though it's non-spontaneous, you can have external sources of energy pushed into the reaction to cause it to happen. But in the case of reactions with negative ΔG, you don't need that sort of thing because it starts on its own, and that's the great thing. So, let's talk about a ΔG of 0. What does that even mean? Well, if it's not spontaneous and not non-spontaneous, it's going to be at equilibrium. It's when a reaction neither moves forwards nor backwards because it's in dynamic equilibrium, where the forward reaction is equal to the backward reaction and nothing happens overall. So it doesn't move forwards or backwards overall. Now, let's do a little refresher. We know that spontaneous reactions go forwards and not backwards. So A to B with a single arrow would indicate a spontaneous reaction that only goes forwards. Now, of course, we know from equilibrium that, of course, there will be some B that will change back to A, but that change is so insignificant that we simply just ignore it and we just say that A goes straight to B because the process of B going back to A is so insignificant that it doesn't even matter. So, in this case, in the case of spontaneity, the forward reaction would be faster than the backward reaction, which overall the reaction will go forwards. And in spontaneity, we are looking at the overall stuff that's happening. So, just remember that. And let's talk about non-spontaneous reactions. Overall, non-spontaneous reactions do not go forward, but they do go backwards instead. So we can take a look at this reaction where water is converted into oxygen and hydrogen gas. We know that this is a non-spontaneous reaction. So we know that it will not actually go forwards, even though this forward arrow is indicating that. So this forward arrow in this case would be indicating that it can go forwards, but since it's non-spontaneous, it's not going to go forwards. It might go forwards a little. But what is actually happening is that the reaction can go backwards. So if you do have these two gases, it will actually react and form H2O. So the backward reaction will happen for non-spontaneous reactions. And because of that, we know that the backward reaction is going faster than the forward reaction. So overall, this reaction should be going backwards. But this reaction is non-spontaneous, so it won't go forwards, but it can go backwards. But if we don't have any of this, it won't go backwards because none of this exists yet. So the only way it could go is forwards. And since it's non-spontaneous, chances are that this H2O will not be converted into O2 or H2 unless it undergoes electrolysis. Now, for a reaction at equilibrium, it is neither going forwards nor backwards because the forward and backward reactions are at the same rate, and because of that, they cancel each other out. So this is just a full review of the very first video about spontaneity. So, of course, at equilibrium, it's neither spontaneous nor non-spontaneous because it's at equilibrium. Now let's do a little example. Solid water, which is ice, is converted into liquid water, which is just water, at 10 degrees Celsius. Do you think this reaction will be spontaneous or non-spontaneous? Well, I think it's going to be spontaneous, because at 10 degrees Celsius, it's above the melting point of water, which is 0 degrees Celsius, so it should melt. So ice should be melting at 10 degrees Celsius into water. So I predict that this solid chunk of ice will melt spontaneously. So this reaction right here is going to be spontaneous. And that means that, well, the conversion of solid water into liquid water will be spontaneous. So the forward reaction is spontaneous. Now, what about this backward reaction? Well, if we know that going from ice to liquid is spontaneous at 10 degrees Celsius, by common sense, the liquid won't go back to a solid at 10 degrees Celsius because 10 degrees Celsius is above the melting point. Everything should be existing as water and not as ice. So this process of turning liquid back into solid won't actually happen because the process of melting will actually happen. So it's something we learned before, but opposite processes will be opposite in terms of spontaneity. So if the forward reaction is spontaneous, then this backward reaction will be non-spontaneous for many reasons. One being that we know that 10 degrees Celsius at 1 atmosphere of pressure, liquid water will not become solid water. And there's actually another reason. Let's take a look at the signs of the delta G's. So we know that a negative delta G refers to something that can continue on its own, so it would be spontaneous. So negative delta G is spontaneous, and positive delta G is non-spontaneous. So in this case, this reaction, since melting ice is spontaneous, this reaction would have negative delta G. Now, the opposite reaction, when you flip the reaction over, we know that from delta H, we know that when we flip reactions, the sign on the delta H changes. It's no different here. The delta G will change in signs as well, and this reaction will have a positive delta G value, and we know that positive delta G values are non-spontaneous. So there are two ways to figure this out, and I think we did an amazing job explaining that. So now let's go on to prove something very important that you will probably have to memorize. So we learned from the last video that the delta X of surroundings is equal to the negative delta H of system over temperature. So check out the last video if you want to know how that is derived, but if you don't care, let's move on. So we know from one of the laws of thermodynamics that the delta S of the universe is equal to the sum of the delta S's of the system and the surroundings, because these two make up everything, and everything is the universe. So it makes sense. And what we can do is substitute the delta S of surroundings for negative delta H of system over temperature. I'm really tempted to say time, but capital T is temperature. So now that we know that, we can multiply everything by T to get T over here, and get T over here and cancel out the T on the third term. Now let's multiply everything by -1, and you'll see why I do that. So multiply everything by -1, and we get this right here. Now, I don't know how this is derived, but by definition, the delta G of a system is equal to negative T delta S of the universe. Don't ask me why, it just is, and it's the definition, so we will apply it. So substituting negative T delta S of the universe, we get that the delta G of the system is equal to the delta H of the system minus T delta S of the system. Notice how everything is in terms of system, and in almost all cases in chemistry, system refers to reaction. So let's just change system to reaction. So the delta G of a reaction is the delta H of a reaction minus T delta S of a reaction. So this equation is known as the Gibbs-Helmholtz equation. And this happens at a constant pressure. And this equation basically tells us that we can increase or decrease temperature, and this will change delta G. Because look, if we increase T, delta G will become more negative, or it will decrease because this term is being subtracted. And if you increase T, you're subtracting a bigger term, and that will decrease G. And note that T is in kelvins, and your ΔG, ΔH, and ΔS should all be in the appropriate units, whether you choose kilojoules for everything, and for ΔS it would be kilojoules per Kelvin, since it has some interesting units going on. But the point is that our reactions, the equations have to have the right units for it to work. So keep things consistent, and we will do an example just to reinforce that idea. So we have to also assume that temperature does not change the values of ΔH or ΔS. So by changing this T, our ΔH and ΔS are constant. And in real life, they actually do change, but they change slightly. And because they change slightly, we ignore the change. So we just assume that ΔH and ΔS are constants, and the only two things that are changing are the T and the ΔG. And note that everything is in knot, so that tells you something that we will review very soon. So we know that we can have ΔG represented in the form of a summation equation, just like how we did it for ΔH⁰, and it means the same thing. When we do ΔH⁰, we can use the heat of formations, and we can do the products minus the heat of formations of the reactants to get the ΔH of the reaction. So check out the video about heat of formations if you want to learn that. But for here, the process is basically the same. The ΔG⁰ is equal to the ΔG of formation of the product. So you're going to add everything up minus the ΔG of formation of the reactants. And you know that just like ΔHF, or the heat of formation, you can find the ΔGf for all the reactions, all the chemicals in the reaction, multiply each by its coefficient from the reaction, and solve for G. Now we will do an example later on, so let's just keep that in the side of our brain and let's move on. And oh yeah, we have to talk about the knot. If you remember, knot stands for state conditions, or I think standard state conditions. So standard state conditions means that we're at 1 molar, 1 atmosphere for all the chemicals involved. And typically we do 25 degrees Celsius by default, but this can actually vary. So watch out for that. Now let's do a little bit of review. We know that when ΔG is positive, it's non-spontaneous. If ΔG is 0, it's at equilibrium. If ΔG is less than 0, we have a release of useful work, which is done on the reaction to move it forwards continuously, and this makes the reaction spontaneous. So now let's talk about the effects of temperature. Oops, that's the erase function. Let's talk about the effects of temperature on ΔG. Now, it actually depends on the signs of ΔH and ΔS. So in the example above, I think what I did was I assumed that ΔS was positive, which was why by increasing temperature, ΔG would decrease. Now that assumption is only true if ΔS is positive, but that's not always the case, and there are many reasons why. So we have to actually take a look at this equation in order to understand why things on this table are true. So let's just start off by saying that the ΔH is positive and our ΔS is also positive. So we have two positives. What do we have to make T in order to get ΔG to be negative? So this thing says that this reaction, if it has a positive ΔH and a positive ΔS, will only be spontaneous at high temperatures. Why is that? Well, we can kind of prove it to ourselves by thinking about what spontaneity means. It just means we need to have a negative ΔG. Doesn't matter what size, we just need it to be negative. So our goal, make ΔG negative. So how do we do that? Well, let's start off by stating what we know. We know that the ΔH and ΔS are both positive, so I'm going to substitute those variables with some positive or negative signs, and in this case, they're both positive signs. So, as we see, we start off with a positive number. So obviously, delta G would be positive if this was the only thing influencing it. And that's not good, because we want delta G to be negative. How do we do that? Well, I think delta S will kind of help us out here. And how will it do that? Well, it's going to help us out because we know that T is in Kelvin, and Kelvin is always positive. So we don't have to worry about the sign of T, since it will match the sign of that. So in this case, this entire term right here is going to be a positive number, and we're actually subtracting this positive number. So our goal is to make this a negative number. So we got to decrease the value of this expression over here to make it negative. Now we start off with a positive, and it's good that we're subtracting by a positive number. Now, how do we make this term or this entire expression as negative as possible? So if we want to make it as negative as possible, in order to ensure that our delta G is negative, which means spontaneous, then what we must do is we must increase temperature. And once we increase it enough at high temperatures, this term will become very large because T will be very large, and you're multiplying by a positive number, and you're subtracting by a very big positive number. So you're going to make this side very, very small. And when I mean small, I mean as negative as possible. So by making T larger, you're making this term bigger, you're subtracting by a bigger number. So you're going to get a bigger negative number the more you increase T. And this means that our delta G will also do the same and become more negative. So look at that. We just proved that at high temperatures, the reaction is spontaneous since it has a negative delta G. Now what about at low temperatures? Well, at low temperatures, it won't be as spontaneous, and it might not even be spontaneous at all. And that's because if we assume T is 0 Kelvin, then this entire term just disappears, and we're left with a positive delta H. And guess what? If this is the only thing that's influencing what delta G is, that's bad, because that means that delta G will be positive, and positive means non-spontaneous. So we can see that if we make the temperature low, this delta G will be positive, and that's not what we want, so it's very bad. So let's now go down here and let's talk about this. So this is a table I made, and we're going to figure out one by one what we have to do to the temperature to make it spontaneous. Does it have to be at a high temperature, such as when delta H and delta S are positive? Does it have to be at a low temperature? Who knows? Let's figure out this second condition over here, when delta H is positive and delta S is negative. Now remember, our goal is to make delta G negative. Doesn't matter how negative, we just need it to be negative. So let's try to figure out how we can make this condition so that we can make delta G negative. So we know that our delta G is equal to the delta H minus T delta S. Let's shove in the symbols so delta G will be equal to a positive number minus T times a negative number. Now there's a problem here. Here we have a negative term. If we have a negative term and we're subtracting a negative term, we're actually going to be adding. So this overall process that we're doing here is actually just adding, because subtracting a negative number is the same thing as adding. Now we're going to run into a lot of tricks here. So if we start off normally at low temperatures, assuming that T is 0, this entire term will just disappear because T is 0, and 0 times anything is 0. So at very low temperatures, we know that delta G will be positive. So at low temperatures, it's bad because delta G is positive, but we want it to be negative. So let's try seeing if we increase the temperature. If we increase the temperature, guess what happens? Things get worse, and the reason is, as you increase T, as T increases, this negative term becomes larger because you're multiplying by a larger number, and this means that you're subtracting by a larger negative number, which means you're adding a larger number. Now when you're adding a number to a positive number, you're going to get a big positive number. And that's bad, because we're making delta G bigger and bigger and bigger. But that's not what we want. So it seems like increasing temperature doesn't work as well. So what do? Well, guess what? If the delta H is positive and the delta S is negative, it will never be spontaneous. So it's always non-spontaneous. And that's because either by low temperatures or high temperatures, the reaction will actually never be spontaneous because of the math we just went through. Now, what about this third condition where our delta H is negative and our delta S is positive? Well, let's do the same thing we did. Delta G is equal to our delta H is now negative. So we're looking at this third row. So a negative minus a T times a positive. Now things are looking good, even at low temperatures. So if we decrease T, who cares? This term over here is negative. And even if this term is 0, as long as we have a negative here, delta G will equal this negative value. And since delta G is negative, then it's spontaneous at low temperatures. What about at high temperatures? Well, if we have high temperatures, this term we know will be positive, and increasing temperature will cause this term to be a bigger positive term, and we're subtracting by a bigger positive number. So we're subtracting by a bigger number, making delta G smaller and, more negative. So if we increase temperature, delta G will be more negative. So that means that even at high temperatures, it will still be spontaneous. So we can conclude that in these conditions, it will always be spontaneous. And we can continue doing this logic, but I think you have enough practice to figure out the rest. So we figured out, I think, these two. And this last one is pretty interesting, because if our delta H is negative and our delta S is negative, it's actually spontaneous at low temperatures. So that's pretty cool. And if you might be wondering, these signs actually matter. So if our goal is to make delta G as negative as possible, what's ideal is to make the delta H negative and the delta S positive. And this shows us that when a delta H is negative or a delta S is positive, it supports spontaneity. So that's a very important thing. A negative delta H or a positive delta S will make a reaction more favorable or more spontaneous. And that's because it makes the delta G more negative. And that's always the goal in this video, to make our delta G as negative as possible to make sure that our reaction is spontaneous. So these two conditions fulfill it. And you might be wondering, why is that? Why does a negative delta H make a reaction more favorable? Well, there's a saying that goes like this. When chemicals lose energy, when chemicals go from a less stable state, so less stable means higher energy, to a state with less energy that's more stable. So when you have less energy, you're more stable, because if you're energetic, you're moving around a lot. If you're not as energetic, you're not moving around as much, and you're more stable. You can think of it like that. But basically, things like to go from high energy to low energy. So because of that, this is actually a decreased energy, or a delta E that is negative. And that idea applies to here. A negative delta H is favorable, because reactions like to go from a higher energy state to a lower energy state. Now, what about a positive delta S? Well, according to the law of thermodynamics that we reviewed up here, the delta S of the universe is equal to this, but we also learned that it has to be greater than 0, which means that entropy has to always be positive for the universe, which means that the universe tends to get more chaotic over time. So the delta S of universe is greater than 0, so that means that the universe gets more chaotic, since we know that a positive delta S means an increase in disorder. So the universe likes to be more chaotic over time. But a positive delta S means that things will get more chaotic, which supports our idea that the universe likes to be more chaotic. So through these two kinds of analogies or references, we conclude that a negative delta H or a positive delta S will make a reaction more favorable because they obey the laws of nature, and we never disobey the laws of nature because they are law. So now that we know that, let's actually move on and talk about some more things. So this is an entirely new equation that I don't know how to derive, but you should memorize it anyways because it's super duper important. So what is this equation? It says that the delta G is equal to ΔG⁰ plus RTlnQ. What an interesting equation. It lets us convert the ΔG⁰, which is at standard state, so, 1 molar, 1 atmosphere, as we said before, not necessarily at 25 degrees Celsius, but it's usually for most cases. So we know that if it's at standard state, that means that everything is 1 in terms of concentration or pressure. Now, this equation basically lets us convert from standard state to basically any state, or when the concentrations are not at 1 molar or at 1 atmosphere. And this is where the Q comes in. That Q over there actually lets us modify these concentrations and pressures to give us the delta G in different conditions. So we know that R is 8.31 times 10 to the negative 3 kilojoules per Kelvin. And yeah, so we know that T is always in Kelvin, and I think everything looks good here. And of course, these two, so I forgot to give you the units for delta G, but delta G is a type of energy, and energy is always in kilojoules, or in joules, but this is kilojoules per mole of reaction, because usually we're looking at reactions, so we might want to add that to be more specific. So I want you guys to memorize this. Now, let's talk about why this equation works. Let's test its durability. So let's just say that we want the Q to be 1. Now, you might be a little suspicious, but what happens is that if you plug in 1 here, the natural log of 1 is 0. So this entire term cancels out, and you get delta G is equal to delta G⁰. And this actually makes sense, because delta G⁰ is when all concentrations are at 1 molar and all pressures at 1 atmosphere. So Q will be 1, obviously, which is what we plugged in. And we know that the natural log of 1 is 0. So we know that the delta G would equal the delta G⁰, because these two mean the same thing. Because if our Q is 1 for this new condition, it's going to basically be that. But it just doesn't have that not sign, but we should add that not sign because it's kind of misleading. So let's test the durability of this equation even more. What if we wanted to make this Q equal to K? Well, something interesting happens actually. If Q is equal to K, then we are at equilibrium. And why is that? Well, we learned in equilibrium, when the ratio between products and reactants is equal to K, then we are at equilibrium. And that's what equilibrium means. So at equilibrium, we know delta G is 0. So this is always the new condition, and this is always the standard state conditions, I think. Right? Standard state, there we go. It is standard state. So we are converting from standard state to a new condition when Q is equal to K. So if Q is equal to K, we know the delta G is 0, because that means equilibrium. So 0 is equal to all this. And we got this new formula that the delta G⁰ is equal to negative RTlnK. Now, I want you guys to be careful about something. We have to also make sure that everything is at the same temperature here. So if you have this at 25 degrees Celsius, you are calculating the new delta G at 25 degrees Celsius. And naturally, you're going to plug in 298 here because that's 25 degrees Celsius in the form of Kelvin once you add 273.15. So just make sure everything is at the same temperature, and let's actually move on. So this equation, you don't have to memorize it because it comes straight from that first equation I told you to memorize. But if you want to, it's super helpful, and I would do it if I were you. Now, just like ΔH and ΔS, you can actually find ΔG via Hess's law. So, why is that? Well, Hess's law applies to things that are state functions, and Gibbs free energy is a state function because C will always have, okay, we actually have to look at the reaction first. So in this reaction, A turns to B, B turns to C, the net reaction is A turns to C. And you can add these two delta G's to get the third delta G, and make sure that all the delta G's are at the same temperature and conditions, or else this will probably not work. Now, let's read on. So we know that Gibbs free energy is a state function because, by definition, a state function is anything that stays the same no matter what path is taken to get there. So it's a state function because C, chemical C, will always have the same Gibbs free energy regardless of the path taken to get to that substance C. Also, since we know that G is equal to H minus TS, and this comes straight from the fact that delta G is equal to delta H minus T delta S, it's basically without the delta S, but we never use this since we can never actually calculate the value of H. We can only calculate delta H, and I talked about that in the enthalpy unit. So down here, we know that since G is equal to H minus TS, and since H, T, and S are all state functions as we've learned before, then delta G is also a state function as well. Or in other words, in terms of Hess's law, the jump in G, so that's a G, or the change in G, they mean the same thing, from A to C will not depend on the path because either through one step from A straight to C, or it's two steps from A to B, then B to C, the energy difference between A and C is constant, since both A and C have a constant Gibbs free energy. And that's why that's why Hess's law works, because it doesn't matter what path you take, the sum of the paths will, equal the final path. So if you didn't understand that explanation about how G is a state function, then I recommend you check out a video about state functions, or one of my videos about Hess's law, which I explain more thoroughly. But in this case, I explained it before, so I'm going to let you do a little bit of exploring if you're curious. But if you're not, let's move on to the final topic, which involves energy diagrams. Now, you might see these in some places, and we've definitely seen these before for delta H when determining whether a reaction is exothermic or endothermic. But in this case, we're looking at G. So in this graph, G is the y-axis, Gibbs free energy. X is time, or over time, we have reactants going to products, and they're changing in the amount of Gibbs free energy they have. So looking at this graph, we see, of course, an activation energy peak, same as for delta H. But the only difference is that we're going to be looking at delta G when we're looking at the difference between products and reactants. So in this case, since the Gibbs free energy of the products, Gp, is greater than the Gibbs free energy of the reactants, Gr, then the change in Gibbs free energy is final minus initial Gp minus Gr. And since Gp is greater than Gr, we will get a positive number, and it will be greater than 0. So we know from this that delta G will be greater than 0 because it's a positive number. So this delta G right here will be positive. And since it's positive, we know it's non-spontaneous. And we have a word for this. It's called an endergonic reaction. So like endothermic for positive, endergonic for, ender is the same thing as endo. They're analogous. So since endergonic means non-spontaneous, it will also indicate a positive delta G. And a good way to remember it is, well, by referring to the prefixes for the delta H's, and you know how a negative delta H is exothermic and a positive delta H is endothermic. So in this case, a positive delta G will be endergonic. And the only difference is gonic, because we're dealing with Gibbs free energy, and it starts with the letter G, like going, right? Like going forwards or not, spontaneity, you get the point. Now this reaction is the complete opposite. We're going from reactants to products, but it's decreasing in Gibbs free energy. So obviously, delta G will be negative. Oops, that's a positive. Let's make that negative. Delta G will be less than 0. So we know that's spontaneous. So now let's take a look at a little more complicated diagram. So this energy diagram involves an intermediate, which is shown here. So this is the reaction A to B and then B to C. So overall, the B's cancel out and you get A to C. So in between, there's a B that goes away, and we know that we call those intermediates. So the intermediate lies in between the hills, and on top of the hills, there are things called, whoa, where did my screen go? Let me go back. On the hill, there are things called activated complexes. They're basically unstable forms of what you had originally, getting ready to transform into the next thing. So that's what activated complexes are. And notice how they're unstable. And that's because they have a very high energy level. And we know that high energy levels typically correspond to low stability. And as you can see, from A to C, we are going from higher energy to lower energy. And that means that the delta G0 is going to be less than 0, or it's going to be negative. And because it's negative, well, this is a spontaneous process. And we can think of it this way. The product C has less energy than A, so it's more stable since it has less energy. And therefore, the path from A to C will be spontaneous because it's going to a lower energy state. So that's one way to think about it. Check out video 9.5 for more details. And this video will include things like catalyst and how they impact the diagram. So if you don't know that, check out the video. Or if you're just curious, check it out as well. Now, let's take a look at ΔGf, or the delta G0 formation. This is the change in G for the formation of 1 mole of substance from natural elements. Sounds just like the delta H of F, or the heat of formation, just for, Gibbs free energy instead of enthalpy. So, we know that the delta Gf of natural elements is equal to 0. And this is because, if you think about it, let's just find the delta Gf of H2. This is going to be equal to 0, because if you write the formation equation, or reaction, it's H2 gas becomes H2 gas. How do we form H2 gas? Well, we use 1 mole of H2 gas, and nothing happens. So therefore, the delta G is 0, because nothing happens. Both of the Gibbs free energy for these two are equal, because they're the same thing. So, they'll cancel out, and if you subtract the final Gibbs free energy by the initial Gibbs free energy, they are the same, so it will inevitably become 0. And that just happened. So let's do a little problem. So here's the equation. Remember, the delta G for a reaction, just like the delta H of a reaction, is the summation of the products formations and the reactants formations, and you're just going to subtract them. So you're going to sum up all the delta Gfs for the products, and you subtract that by all the delta Gfs of the reactants. Let's see how that works. It's really similar to how we do delta H, and we use delta H0 of F. It's basically the same process, and that's why I'm not really going to go too much into detail. So for this reaction, 2A becomes B plus 3C. I know that's kind of hard to see. And I give you the, well, let's put the F's there just to be more specific. I give you the ΔG formations for each of these chemicals. So we know that we have sum the products and subtract it by the sum of the reactants. So our products is B, so since there's only one B, it's going to be 1 times B plus 3 times, well, the ΔG formation for chemical C is just lowercase c. And we're going to subtract that by the total amount of ΔGf for the reactants. Well, it's just going to be 2 times the ΔGf of A, which is lowercase a. So let's simplify that. So it's B plus 3C minus 2A. This is the expression if you wanted to solve for the ΔG. And if we had numbers for A, B, and C, we could totally solve this. But that's not the important part here. The important part is just knowing how to do it. Now, I forgot to mention this, but I want to show you one last thing that's super important that I kind of forgot. Based on this equation over here, ΔG now equals negative RTlnK, we can conclude that when K equals 1, we know that the natural log of 1 is 0, and therefore ΔG naught will be 0 when K is 1. Now, if K is greater than 1, this number will be a positive number, and you negate a positive to get a negative. So, if K is greater than 1, the ΔG naught will actually be negative, or it will be less than 0. And the opposite is true as well. If K is less than 1, this will become negative, and negative and a negative is positive. So therefore, ΔG naught will be positive or greater than 0 whenever K is less than 1. Super important stuff. Now let's do a practice problem. So let's begin. Let's just have an arbitrary reaction, and the delta S naught of a reaction is 99.0 joules per K times mole of reaction. The delta H naught of the reaction is 12.00 kilojoules per mole of reaction. I want to find the ΔG naught of the reaction at 100 degrees Celsius. Now remember, the naught just means everything is at 1 molar or 1 atmosphere. It doesn't necessarily have to be at 25 degrees Celsius. In this case, it's 100. So let's use this famous formula that we are going to memorize. Alright, now we just need to solve for this. So we chug in the numbers. Delta H is 12.00 minus T, which is 100 plus 273 is 373. So 373 times delta S naught. We have to convert this into a scientific notation because we have to convert this to kilojoules to match the units. So these are all in joules. This is in joules actually, and we want it in kilojoules. So 99.0 joules per K times mole of reaction. We want it in kilojoules, so we know that there are 10 to the third joules per kilojoule. So essentially, we just got it. So in the end, the delta S will be, let's see, 99.0 times 10 to the negative 3 kilojoules per K times mole of reaction. Now, I wrote the units there just to show you that we need kilojoules because everything else is in kilojoules. Now, doing the math, let's see what we get. 373 times 99 times 10 to the negative 3. We actually get minus 36.9 there. And let's just put an extra sig fig there, but it's at 366. And this is 12.00 minus that. So let's see what happens then. What ends up happening is that we get, let's see, so 12 minus 36.93, we get a ΔG naught of negative 24.9. And this is in kilojoules per mole of reaction. Same units as delta H. Now, let's move on to the next question. Find the maximum T for which the reaction is non-spontaneous. Or in other words, what is the maximum T before G stops being positive? Because it wants to find the maximum T for which the reaction is non-spontaneous. So let's think about what that means. A reaction is non-spontaneous when the ΔG⁰ is greater than 0. So we know that the ΔG⁰ is going to be ΔH⁰ minus T ΔS⁰, and this has to be greater than 0. Let's chug in our numbers again. So let's see, what number should I chug in? I know the H is 12.00 minus T, so we're changing the T, so we're not going to plug in anything for that, but we know the ΔS⁰ is going to be 99.0 times 10 to the negative 3, and this is greater than 0. And note that I matched the units, so this is in kilojoules per Kelvin, that's in kilojoules, and everything is great. Now add it to both sides, 12.00 is greater than T, and I'm going to divide both sides. Actually, before I do that, let's just write everything so I'm not confusing. Alright, so 12 divided by 99 times 10 to the negative 3. I get, let's keep track of sig figs, 121 is greater than T. So it looks like as long as T is less than 121, our reaction will be non-spontaneous. But when we go above 121, it'll be spontaneous. So it looks like the maximum temperature for which the reaction is non-spontaneous is going to be 121, because the temperature can at most be 121 according to this inequality. Because if we graph this, we can see that T is going to be less than 121, so like that. And notice how the maximum is going to be at 121. And anything to the right is going to be actually spontaneous, but over here it's non-spontaneous. Alright, let's try to find K at 25 degrees Celsius. Well, we do have the ΔG⁰ at 100 degrees Celsius. That's not the same temperature. We need to find the ΔG⁰ at 25 degrees Celsius, because we got to make sure that the ΔG⁰ and the K are at the same temperature. So this is going to be our ΔH, which 12.00 minus T 298 times the S, which is 99.0 times 10 to the negative 3. And doing the math, 12, well actually let's simplify to make sure our sig figs don't go wrong. Times 99.0 times 10 to the negative 3. I get 29.5, 29.5 is right. 12 minus 29.5, I get, let's see, negative 17.5 is equal to ΔG⁰ at 25 degrees Celsius. Now we can use this equation. ΔG⁰ is equal to negative RTlnK. And remember how I said that these have to be at the same temperature? Well, we did it. Now we just have to solve it. So we know ΔG⁰ at 25 is going to be negative 17.5. Set it equal to negative 8.31 times 10 to the negative 3. And we use this number because we're doing kilojoules. T is 298 lnK. And all that's left to do is some algebra. Negative 17.5 divided by 8.31 times 10 to the negative 3. And we divide by 298. Let's see. So I got 7.0, let's see. 7.07. Well, let's do this. 0.67, so 3 sig figs is equal to the natural log of K. Now we're going to E that. So E to the 7.067 is equal to the natural log, equal to just K. So we use our rules, and we know that the number of decimal places is the number of sig figs. So let's see. E to the answer will give us a K that's equal to, let's see, 1.2 times 10 to the third. Boom, we're done. So that's all for this video. I hope you learned a lot, and have a wonderful day, everybody.